in this section, we're going to be looking deeper into the causes and the effects of gravity. And to do this, let's start by talking about free fall. We've already begun working with free fall, so let's look into this a little bit. So when we talk about gravity, we know that it is a non-contact force. So if you have the moon, for example, and it's orbiting Earth, we know that these two bodies have a gravitational effect on each other, and they're not touching. So obviously, it's a non-contact force. And gravity is the interaction between any two objects having mass. So it could be two people standing next to each other, or what we're more familiar with would be, say, a smaller object and a planet, but really gravity acts between any two objects with mass. So a force caused by gravity is what causes free fall. And the effects of that are then that we accelerate towards the ground if we're in free fall. So if you are going skydiving and you jump out of an airplane, you're always under the effects of gravity due to the gravitational force from the Earth. And as soon as you jump out of the plane and you start your descent, then you're in free fall. And we've learned that the acceleration due to gravity in these cases is 9.81 meters per second squared. This is the same whether you're jumping out of an airplane or if you're on the Earth. They're very, very close to 9.81 meters per second squared. But this is, in fact, dependent on the distance between the two objects. But if you're in free fall above the Earth, the distance between you and the Earth is so much smaller than the distance between you and the center of the Earth that the difference between you and between the Earth is minimal compared to that distance between you and the center of the Earth. So while the acceleration due to gravity might change based on distance, and in fact it does, the difference is so minimal when we're talking about small distances between us and the surface of the Earth. So the Earth is so large that even if we're some distance above the Earth, like if we're skydiving, then it's not going to make that big of a difference. So skydiving is, an example where G is still very much going to be close to the same value, whether you're skydiving or whether you're in fact standing on the Earth. The differences are going to matter when we talk about something like the International Space Station. The International Space Station is much higher above the Earth than we would be if we were skydiving or even flying in an airplane. The International Space Station is approximately 1/16th the radius of the Earth away from the ground. So the Earth is very large, and if you would divide the Earth's radius into 16 pieces, well, one of those pieces would be the distance between the ISS and the ground. So this is much, much greater than the distance that you would be if you were skydiving towards the Earth. So gravity, this acceleration due to gravity does in fact change depending on where you're located. But in most cases, when we deal with objects close to the Earth, this value, the acceleration due to gravity, is going to be very, very similar, even if you're on top of a tall mountain or if you're close to sea level. So then this brings us to discussing position and weight. So weight is the force that we experience that's due to our gravitational attraction towards the Earth. And we know that the weight force is equal to the mass of an object times the acceleration due to gravity. Again, this is the case when we're pretty close to the Earth. This value of G doesn't change very much when we're close to the surface of the Earth, but this value of G probably wouldn't be good to use if we were on the space station, on the ISS. But we find then that the magnitude of the gravitational force is inversely proportional to the square of the distance between the centers of mass of the Earth and the object. And what does that mean? So we're saying that the magnitude of the gravitational force. So I'm just going to say generally the force due to gravity, I'm going to say the magnitude of this, where it's going to be inversely proportional. So inversely proportional means 1 over some value. And this little symbol right here, this means proportional to the little fish symbol. I think we've been introduced to that before, but just to mention it again, this is proportional. And we're saying now that the magnitude of the gravitational force is inversely proportional to the square of the distance between the centers of mass of the Earth and the object. So the square of the distance between the centers of mass of the Earth and the object. So now we're not dealing so much where this case, where we deal with little g, we're assuming that we're somewhat close to the Earth. But now you can choose any distance between two bodies and you can actually figure out the force of gravity between them. This R value can be anything. So you could have now, for example, a much more reliable way to measure the gravitational force between the Earth and the International Space Station. And again, the R value, this radius, would be between the center of the Earth and this object. So it would be the center of this object and the Earth, and this radius here, this would be the R value that we're discussing. It's this distance. And notice we haven't actually gone into the formula for the force of gravity between two objects. We're just discussing generally what this relation looks like, and it is shown to be proportional to this 1 over r squared relationship. So if you increase this r value, if this r value goes up, if we get further and further, if we get even further away than the space station, if we're out here, maybe some satellite that's far above the Earth, well, as r gets larger, the force of gravity gets smaller. And that is the case between objects. The further apart they are, the less the force of gravity there is between those two objects. So it's never zero, but it approaches zero. So, for example, the planet Neptune is very far away from us, but there is a calculatable force of gravity between you and the planet Neptune or any other object in the universe. It's just a matter of plugging it into this relationship and seeing what the proportionality is. And when we actually go to graph this relationship, this 1 over r squared relationship, which is very common in physics to find forces that have this sort of relationship. Well, if we're exactly, now I'm looking at this top graph here, and the way I've written this out, so we have this weight force on the vertical axis, and on the horizontal axis, I'm counting 1, 2, 3, all the way to 10 in Earth radii. So this r sub e, this is indicating radiuses of the Earth. So if we're at 1 Earth radius, where are we located? Well, if we're at 1 Earth radius, we're on the surface of the Earth, approximately. It's going to vary depending on whether you're on a mountaintop or at sea level, but generally you're going to be at 1 Earth radius. And if this is a 1 kilogram object, I'm going to discuss this 1 kilogram object here in both these graphs here in just a moment. But if we're considering a 1 kilogram object and it is at 1 Earth radius, well then what is the weight force? And we can just go back to here to the formula for the weight force, and we know what little g is. It's approximately 9.81. So the weight force at 1 Earth radius for a 1 kilogram object is going to be 9.81 newtons. It's going to be the mass, which is 1 kilogram. So let's write this out. It's going to be 1 kilogram times g, which is 9.81 meters per second squared. And this is the weight force. Well, when we combine these, we know a newton is defined as a kilogram meter per second squared. So the weight force for this 1 kilogram object is 9.81 newtons. And that's here at 1. That would be at the surface of the Earth. So it would be just under 10 would be this point right here. And what we'll find as we start to increase Earth radii, as we start to get, so this would be, this 2, for example, would be the distance of the radius of the Earth twice. So if you'd go from the center, the core of the Earth, to the surface, and then you'd do it again, well, this would be equal to the diameter of the Earth. So that's just one way of expressing this distance. And what you'll find is that if you go 2 Earth radii away, that force for that 1 kilogram object is just slightly over 2. So this is 5, so it'd be slightly over 2. So notice this force drops very quickly. And that's the nature of this 1 over r squared relationship, because it has this square to it. So if you put in a number, it's going to get squared. It's just going to get larger. And the larger this is, the smaller the force is. And if we continue on here and we just put in a couple more values, it starts to decrease very quickly. So 3 Earth radii would be roughly about here. And 4 Earth radii would be down here. And it would just continue. So if we would connect these dots, and I'll try to do this carefully here. If we would connect these dots, we would find very quickly that the force begins to drop rapidly as we get further and further away from the object in question. So this is 2 objects. They keep getting further and further away, and the force of gravity between them approaches 0. And that's the nature of a 1 over r squared relationship. It drops very quickly. So another way to describe this relationship, and this one's going to be a little bit more complicated, but I'd like you to just bear with me and just try to think about this the best you can. We're going to try to show this linear relationship between weight versus a 1 over r squared relationship. So this isn't, say, having weight as a function of r equal to 1 over r squared. That's not what we're showing here with this graph. And once again now, these units, when I look at 1 over r squared, this is going to be in terms of 1 over the radius of the Earth squared. And this is actually going to be the units. So what does this look like, for example? So if I take 0.2, the meaning then of the 0.2 on this graph is 0.2 of units 1 over the radius of the Earth squared, which would be, well, how is another way to express 0.2? That's 2/10. So this is equal to 2 over 10, 1 over the radius of the Earth squared. And this can be rewritten 1/5, 1 over the radius of the Earth squared. So now what we've done is now we've increased the distance. When we're at 0.2 on this graph, we're actually talking about a greater distance between whatever these 2 objects are. Because you can see here now we have this factor of 5 in the denominator. So as we've increased the distance, well, what happens to the force? So we're at this 0.2, and the force is much less than we would expect. And what am I saying when I'm saying when we expect? Well, look at when we have a value of 1 on this horizontal portion. What does that mean? So that means 1.0 of units 1 over radius of the Earth squared. Well, this is just the regular case of 1 over 1 times 1 over the radius of the Earth squared. So if we're at 1 over the radius of the Earth squared, well, then the force that we expect is our regular weight force. And when we're at 1 Earth radius, what's the weight force? Well, it's approximately just shy of 10. So that's where we would expect it to be. So as these numbers here are smaller, as we get further away from 1, 0 0.8, 0 0.6, 0 0.4, as these numbers decrease, are actually indicating that we're further away than the distance of one Earth radius. And I'm just going to show just one other example then. So just to be sure this is clear, if we take the middle here, 1/2, which is 0 0.5, so that would be right about here. 0 0.5, another way to write it, is 1/2. And our units are 1 over radius of the Earth squared. Now, what does this actually mean physically? This value that I have here, 1/2 times 1 over the radius of the Earth squared. Well, this is 2 times the radius of the Earth squared. So this would be double the radius of the Earth squared. So what could we expect then if we're that much further apart? In other words, if this is the radius of the Earth, well then this is 2 times the radius of the Earth. And we expect the force to be 1/2. And that's about where it is right here. It's just shy of 5. So this shows that there is a linear relationship when you plot the weight force due to gravity versus the 1 over r squared relationship. We actually see a linear relationship. Now, that's kind of complicated. And if you're not 100% clear on this second graph, that's okay. Don't worry about it. It's a little bit abstract. The more important graph is this top one. The top one shows us an inverse relationship between force and its 1 over r squared behavior, where we see this steep decrease as you get further and further apart. This is the more important graph that we're going to be studying. I just wanted to show this other one. It's in the textbook, and it does show that there is a linear relationship when we plot the weight force versus a 1 over r squared.